Alright, so let's go back to the zombie example, okay? And then I'll have some more real life problems to show you as far as even buying houses and investments here in just a bit. Okay? And then I'm going to ask you some big concept questions near the end to see what really did you learn from today's lesson. So what patterns do you notice in the number of zombies turned each day as the days go by? What happened, guys? What were the patterns? And some of you, like, you already see it, but I want to go through this very meticulously just to ensure that everyone's getting it to that level that they need to. But don't overthink these. If you understand it, please don't overthink it. Just go ahead and let me know. What patterns do you notice in the number of zombies turned each day as the days go by? What would you say? It was multiplied by 3. So it was tripled each day, right? Alright, so let's go ahead and write that down. It was tripled each day. Multiplied by 3, basically tripled each day. Okay, so with it being tripled each day, let's go to number 2. Number 2 says, what would this data look like on a graph? Sketch a graph for the data, and so on and so forth. So what we're going to do is, we're going to pick some points on a graph, and let's go with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10. So here's 9, here's 1. And then going up here, 1, 2, 3, 4, 5, 6, 7, 8, 9, then 10 is up top. Okay? These are the number of days, and these are the number of zombies. And we're going to actually do this as 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100, and these are in thousands. So in thousands, if you will. How many do we have at first? 5. So 0 goes way down here at just 5. Remember, these are in thousands. This is 10,000, 20,000, 30,000, so on and so forth. Basically, it stayed so little until around 7 days we were at 10,000. At 8 days we were about 30,000, and at 9 days we went all the way up to 100,000. So it stayed, and all of a sudden, bless you, it just shot up. Exponentially shot up. So how many days, or how many zombies were turned on day 10? From the table up top, what did we put for day 10? 295,245. Okay? And if you wanted to make sure on that, just with the math, you could go back to the calculator, and you could go to that equation that we built together. Okay, that equation was, we start with 5, we tripled each day, and we could see what was it to the power of 10. Okay, so we have 5, oops, let me try doing that again. Just to capture it. I don't know why there's a connection error. But anyway, go ahead and put that into your calculator, guys. And please make sure that it is in fact that. I might have grabbed yours, I don't know. So it was 5 times 3 raised to the 10th power, and sure enough, 295, 245 is what it gave us. Yes, that is correct. Okay, Alright, so now B says, what would you have to multiply this number to get the number created on day 11? Anyone? 3. C says, how would the entire table change if instead of starting at 5, we only started with 1? How would that change? Instead of starting with 5 zombies, 5 infected zombies, we only started with 1.
The equation was 5 times 3 to the power of x, so it'd just be 3 to the power of x.
Yep, it would be 1 times 3 to the power of x. And you're exactly right. Or just 3 to the power of x. Which brings me to something important, huge, right now. If this is my equation, is this the same as that? No. Why?
Because the exponent has to be applied to the...
There you go. The exponent has to be applied to the 3 first, and then you multiply by 5 because of PEMDAS. We have to do the exponent first and then the multiplication that exists right there. Okay? That's a big misconception. Okay? Let's go ahead and go to D. How long would it take now for the zombies to take over the world? Let's say that there are 6,975,000,000 people in the world, which now there's closer to like 8 billion. And we started with 5 zombies. How long would it take to take over the world? Well, how do we set it up?
That number equals...
It'll be this number is equal to, go ahead. 5 times 3 raised to the power of x. And our answer is x. Okay? So for right now, I'm going to show you 2 different ways. You can do this and menu solve feature to see what would I get. You know what I'm saying? So let me show you something real quick with the calculator, because I want you to know how to do it with the solve feature, but also I want you to know how to do it. I need you to know how to do it by hand. Okay? So let's go back over here. Let me get my calculator out. And if I did this menu solve feature that you see right here, okay, it would look like this. Menu 3-1, and I'm going to solve for 6,975,000,000 is equal to 5 times 3 raised to the power of x. Kick over to the right and do comma x. And then press Control Enter. Press Control Enter so that you get a nice, pretty decimal. And how long did it take? 19.166 days. That's it. 19.1666 days, or 661 days. That would be x. That's pretty fast. We're just starting with 5. Okay. Now if I did this by hand, you're going to learn that if I have 6,975,000,000 is equal to 5 times 3 to the power of x, well, I could divide both sides by 5 to get rid of this. And then now it's just 6,975,123,123 divided by 5. Okay? So if you punch this into the calculator, it will give you 1395,123,123. Let me make sure on that. 123,123. So 1,395,000, or 1,395,000,000 is equal to 3 raised to the power of x. Now you don't know it yet, but the way to solve this exponential graph, you're going to learn here throughout this unit, is to rewrite it as a logarithm, which is in this case log base 3 of 1,395 this is equal to x. You're going to learn that this unit. You won't learn it. You're not necessarily having to know it today. But I just want you to see with where we're going. So if we were to go over here to our calculator, it would look something like this. I would press this button here next to the number 9. Whoops. And I would find the log. And the base was 3. And then I'm going to put this right there. Again, I have to press Control Enter, and it'll give me the same decimal. Okay? Alright, so let's go back. Which one of the equations below would correctly model the number of zombies turned each day if you start with 5 zombies? Guys, which one of these, 1, 2, 3, 4, or 5, would do this correct? If you say again? 1. We already know it, right? We're way ahead of the game. You learned it really, really quickly. Can someone tell me what this one is talking about? What's if you start with 3 zombies and you turn it into 5, multiply by 5 each jump. Okay. How about this one? How many, listen, how many do I start with on this one? Not 5, not 1, not 0. There's one more guess. Remember, when you start, what number goes in for x? 0. So put 0 in for x, and what do you get? 6. You would start with 6. You with me? You're tripling each day, and then you have these 5 zombies that are off to the side that you're just adding to the mix. It's like those 5 zombies are like caged up, and they're not infecting anyone. They're outside of the equation, but they're just there all caged up. You see what I'm saying? You're still tripling each day, but then you have these 5 stragglers that they're not turning anyone. You with me? And it's because they're being added. Okay? Alright, just to contemplate equations, and I wanted to get your brains wrapped around that kind of stuff. Any questions? Okay, so let's keep going. Let's go to 5. What does the unknown variable represent in this equation, guys? Number of days. Write an equation model to model the pattern if instead 12 zombies were in the sleeper cell initially and had the ability to run so that they would infect 6 people per day. And then how long would it take to infect the world? So what's my equation?
12 times 6.
Yep. And now we want to infect the world, right? So we're going to set this equal to the 6,975,000,000. And we want to, for now, let's do the solve feature together. Okay? So we'll go to the calculator. We're going to say 6,975,000,000. And it's equal to, whoops, menu 3.1. Set this equal to, what was the initial value again? 12? Times 6 raised to the power of x, right? Okay. And then we'll just do comma x here at the end and Control Enter. So instead of 19 days to affect the world, because they can run, and you've probably seen movies on this, they can infect the entire world in just 11 days. So these pandemics or whatnot can break out pretty fast. They start slow, but they can break out pretty quickly. Okay? Alright. So, how long would it take? This one would be 11.263 days. Let's go to 7. If you were given the choice of between more initial zombies, but slower growth rate, or fewer initial zombies, but a greater growth rate, which would you pick and why? Say again? So you're saying the same thing, bigger growth rate or the runners, right? You're saying which number is the most important? A or B? B. B is the most important. A is still important because it does affect how many we start with, right? A just makes the growth happen sooner, but B makes the growth happen bigger. You with me? Okay. And what is X? What does that represent? Number of days, number of years sometimes, weeks, whatever you depict it to be in your model. Okay? All right. So now we want to do the antidote. That was growth. Let's do decay. Okay? We did this. And can someone tell me, why did this equation, why did it grow? Why? What about this equation said it would grow? Not the exponent.
The B is
The B is,
it's not decimal, it's a whole number.
it's a whole number, but it's bigger than what number?
1.
1. It's bigger than 1. Because 1, if I multiply it by 1, it's nothing happened. It's like a vertical stretch compression. Nothing happened. But this 3 is bigger than 1. It almost feels like it was vertically stretched by a factor of 3. That's not what's going on, but I kind of want you thinking along those lines. It's bigger than 1. That's why it's growing. So now, if this number is, what would make it decay? Otherwise, not grow, but decrease. Not a negative. A decimal that is between 0 and 1. So a number that is between 0 and 1, guys, can it be 1? Nope. Can it be 0? Nope, because it would zero everything out. There wouldn't be any 1. So it has to be a number in between 0 and 1 to decay. Alright, so let's go to this example problem that we're looking at right now. And it says, for the antidote, it has, within 3 days of the initial attacks being reported, a group of scientists quickly began working to find an antidote for zombieism. Within a few short weeks, they were successful, but unfortunately their antidote was found to only be successful 15% of the time. Make a table showing how many zombies were cured after 10 rounds of administering the antidote, assuming every remaining zombie is given the antidote in every round and no new zombies are created. No new zombies were created. Because then there's a lot going on. You have increase and decrease kind of happening at the same time, and that's calculus. Okay? So, let's start applying the antidote. What will I multiply this number by in order to get my day 1 number? Not 0.15. I see what you're saying. I see what you're saying. This is what a lot of you tend to do, and I tutor a lot of SAT and ACT, so I hear this a lot. The way you see decrease is you multiply this by 15%. Okay? So you'll say 6,975,000,000. So I'm just going to do E6, because that will give me 6 zeros. Okay? And you will multiply it by 0.15. And then you will take that and you will subtract this to get, this is my number. Raise your hand and be honest if you would have done that. Okay? A lot of people probably would have. But the best way, the most efficient, especially the way you're tested, SAT and ACT, to see a decrease is about concentrating on the original amount you start at is always 100%. You with me? But now I'm about to decrease. So it's going to be 100% with a decrease of 15%. You with me? Showing that it should be 85%. So in our equation, we're going to start with 6,975,000,000. But instead of multiplying it by 3 to triple, we're going to multiply it by a number between 0 and 1, which shows a 15% decrease. You with me? So if I did this for day 1, look at what it gives us. Okay? I'm going to go over here to 6,975,123,123 times 0.85 raised to the power of 1. I get the same exact number. This is much more efficient, and the way you're tested, it's easier to get these answers if you're thinking about it from 100%, aka 1.00, is your B value that doesn't change. No growth, no decay. If it's above 1, it grows. If it's less than 1, it's decaying. Nothing to do with the negatives whatsoever. Okay? Alright. So, if you were to go back over here and fill out this table, just to help you out real quick, I'm going to help you know how to use the calculator a different way as well. We're going to build this to give it real quickly my answers from 0 all the way to 10. Okay, first of all, we already know this x. Go ahead and write this in. It's 975 million over here, and it's multiplied by 0.85 raised to the power of x. Okay, that is the equation that I'm going to use now to go to the calculator. Menu 1 4 OK, menu 1 5 to clear. Control dock and adding a calculator graphing page. I'm going to put 6,975,000,000, and it's multiplied by 0.85 raised to the power of x. Whatever the graph looks like, I can't see it. But if I press menu and I'll go to zoom and I try to fit it by pressing A on my calculator, it will try to fit as best as possible this model. And look at these numbers. These numbers are ridiculous as far as what they represent. This 3.88 E with a 10 is the same as 3.88 times 10 to this highlighted orange 10 power. So this E, just so that you know, this E means times 10 to the power of. Okay, so that's a pretty big number. This number is not like 3.5. It's a lot bigger than that, the scale wise. So from here I can press Control T for a table. From here I can press Menu, Table, Edit Table Settings, and I can say the input, the independent variable x input, let's change it to ask. And it almost is going to be like we've done before when I saved and stored the function. And I could put 0, 1, 2, 3, 4, 5, 6, 7, 8, so on and so forth. And it will show me all the values, that I could then put into the table. Okay, so all those values would end up becoming, would end up going into this table right here. A quick way to do it. Another different way. Questions? All right. So, and what patterns of decay do you notice in the cumulative number of zombies remaining after each round? Is that if 15% of it, how many remain? Basically, what we already did, you're just showing it but in graph form. So you can do a quick sketch. You don't have to get too crazy about it. But you can do a quick sketch as far as showing that we came up with your initial number, and it was 1 minus 15%, and raised to the number of rounds administered. Or the initial number efficiently just getting to it, saying that it's decreasing because that number is less than 1. The rounds, let's say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These are the rounds of the antidote. And these are billions of zombies. So zombies, but in billions. Just put it on my desk. Okay. So now I have 1, 2, 3, 4, 5, 6, 7, 8, 9. And at 0, it's pretty close to this 7 billion mark. And then it just starts decreasing where 9 is about 1.2 billion. And it kind of does this. Is what you'll see. That's kind of poorly drawn. Let me draw that a little bit better. It does something more like, come on back arrow, something like this. Okay? That's what the graph is doing. Alright, so number 9, that's just the sketch that I showed you as number 9. Let's move on to number 10, where it says write an equation to model. Well, we kind of already did that. Number 10, guys, is just plugging in that number. 6975 with 6 zeros, and then 0.85 raised to the x power. That's for number 10. Okay? Now let's go to, we're almost done. Just have 3 more. Let's go to 11. At this rate, how long will it take the scientists to completely turn all zombies back into humans? What do I do? What am I going to do with that equation? Set it equal to what? 0. So we start with 6,975,000,000. We are decreasing right here by 15%. It's exponentially growing, and we want to see it will result as 0. So now I'm going to solve this and look for x. Okay? Here we go. Let's go to the calculator. I'm going to get rid of the table by pressing Control T. But I'm also going to press Control Left because I want to go to the first page. If I press Control Up, you can see all the pages, just FYI, and you can toggle over and press Enter. Just trying to teach you the calculator. Control Up, go to the left, and you can go home. Menu 3-1, 6,975,000,000 is equal to, oh sorry, let me come back over here. 0 is equal to this. Times 0.85 raised to the power of x. And we want to comma x. Why did I get false? It's impossible to get to 0. Because if you're taking 15% of something off, you are creating 85% of what it used to be. So think of a person, one person, and if you 85% of that, can you ever get that last one person to 0? No. You see what I'm saying? No matter what you do, it will approach forever. It's almost like carbon dating and whatnot. You know what I mean? Like you learn in science, when things are decaying and whatnot, they can never fully decay to non-existing, but they will infinitely approach wanting to. You've probably learned half-life. Raise your hand if you've learned half-life in like chemistry and stuff. Yeah, so that kind of stuff. You can never fully go to 0.
So, what if you change how much you administer?
It does, well, even if you're administering, the only way that you could do it is if it was 100%. But you're not going to be able to do that.
And then what if you gave them like 200 shots?
So you're changing the percentage to what?
Like, so if you're giving them 1 shot each day, and only 15% coming out.
So you're saying you want 100% to come out?
I'm saying, what if you change it to you're like giving them 200 shots? Like
So the number of shots really doesn't matter. It's still going to just still be the 15% of. Let's say that instead of 15%, it was 50%. It still won't work. Let's say that it was 75% affected. That means it reduced by 75. It still won't work. Let's try 100% effective. You see what I'm saying? X is greater than 0. That's if and only if. Like X has to be greater than 0. You see what I'm saying? So it goes back to that carbon dating, that half-life-ish. You can't ever fully get to it. It's something called a horizontal asymptote. So if we went back to the graph, and you saw the graph went like this, where it starts, it kept going, but then it can't hit 0. Y equals 0 is this horizontal asymptote. You'll learn this, okay? Especially in pre-cal. You never could reach it. You'll get infinitely close, but you could never actually touch it. Okay, let's go to 12. 12 says, what similarities and differences do you notice in the equations developed for both the initial and the antidote phases? So what we have is basically the similarities and differences. The similarities is that they both had an initial value and a rate of change. They both had this and they both had this. But one of them was increasing while the other one was decreasing. So the one that was increasing was because it was 3. B was 3. The one that was decreasing because B was what?
B was
Greater than 0 but less than 1. It was between 0 and 1. Still positive. Okay, so number 13, what number in the equation impacts whether or not the initial value will increase or decrease? It is the B, so I kind of went a little bit ahead. If B is greater than 1, then you will increase. But if B is between 0 and 1, then you will decrease. Any questions? All right. Stop there. We have one more